So this is our third presentation. The first two presentations I'll cover in just a second, but this one is collaborative innovations in sustainability, environment, and agriculture. The last two presentations, the first one was about materials, defense, and energy, and the second one was about therapeutics, health, and nutrition. There are recordings of the first two. There will be a recording of the third one as well. That recording can be reached by going to technologyideation.com or going to Biosortia or reaching out to Biosortia directly. So what we're going to talk about is industrial scale microbiome mining and what that actually means moving forward. So this next slide is just a quick overview of the technology. And hopefully we'll be able to run this YouTube video seamlessly. We'll find out. Here we go.
Territories of natural microbiome. Depth of oceans lies a hidden treasure trove of potential. Mysterious molecules with the power to revolutionize medicine, agriculture, and technology. For decades, scientists have been on the quest to unlock these secrets, often referred to as the dark matter of biology, with limited success. Traditional methods have stumbled, finding themselves unable to culture or even identify the myriad of life's building blocks hidden within these microscopic communities. Enter Biosortia, pioneering entity at the forefront of scientific breakthrough, promises to change everything through the development of a groundbreaking technique known as industrial-scale microbiome mining. Biosortia has shattered previous limitations. This innovative approach doesn't just skim the surface, but dives deep into the microbial cosmos, retrieving natural molecules, those elusive off-peak and sub-peak entities, in quantities ripe for research. Imagine unlocking the potential of the uncultivable, bringing to light new small molecules of enzymes, an exponential pace reminiscent of nature. This is not merely a step forward, but a giant leap in our understanding and utilization. The implications are staggering. Flood of novel molecules now accessible for the first time, fueling next-generation therapeutics, expanding the arsenal of medicine against diseases yet undefeated. Moreover, this wealth of information becomes a veritable goldmine of artificial intelligence, populating vast data sets that drive discovery at speeds previously unimaginable. Screenable quantities of these novel entities pave the way for early preclinical work, accelerating the journey from concept to cure. This is the dawn of a new era in biotechnology, heralded by the advent of industrial-scale microbiome mining. With the fusion of cutting-edge ML/AI technologies and an innovative approach to extracting and processing natural aquatic microbiomes, hundreds of thousands to millions of novel molecules are now within our grasp. Pursuit of understanding and leveraging the unseen and uncountable microbes that share our planet has entered a new phase, promising solutions to some of humanity's most pressing challenges and opening doors to opportunities we've yet to imagine.
So sorry about that choppiness. I think I'd love to be able to blame it on solar flares this week, but I may not be able to blame it on that. What we're really talking about is what science has had a very difficult time getting to for the last history of research, to tell you the truth. We certainly understand that the small molecules that are in nature are involved in things like cellular signaling, turning things on, off, up, or down. But there is an inability to get at the vast majority of these molecules. And that's really what this technology of industrial scale microbiome mining is supposed to be able to do. And we've been able to prove we can do that. And then the opportunity, we talk about utilizing the aquatic environment as a source. And that's part of the reason that this works so well, is all microbes are interconnected. We do a good job in our first presentation talking about that interconnection, and then we review it a little bit in our second presentation. So I'm not going to spend too much time on this, but the reality of it is even the aquatic environment overlaps our human microbiome by approximately 73% in genes and metabolic pathways. And the molecules are residing within a human at such a low concentration level, they'll never be discovered directly within the human. And this is where industrial scale microbiome comes in, microbiome mining comes in, is because we're not starting with a small sample. When you look at the top left and you see that 100 milliliters as a beaker sample, that may be typical in a research environment, starting to look at biomass and understanding what that chemistry might be. But if there's molecules in parts per billions and parts per trillions, there's a strong possibility they'll never even be measured, let alone figure out what they are. So Biosortia starts with 200 million times that sample size. And what you see in the bottom of these pictures is a couple different scales of that technology. We call the one scale scouting. That allows us to go virtually anywhere and look at a microbiome on the scale to start to understand what the molecules are and potentially even start discovery. Typically, a microbiome is a very rich source of opportunity, and that's where the full-scale harvesting comes in. And on a full-scale harvesting, we can go even much deeper. We'll talk about that in a second. In the future, we see this technology expanding dramatically. No one would mine lithium with a beaker. And certainly the molecules of lithium or the molecules of gold or other opportunities are very valuable. The molecules that have not been discovered that can come from the microbial world, from biology, whether inspirational, direct, or indirect, could be billion-dollar molecules. There could be more than $1 trillion of molecules yet to be discovered that exist within the molecules of a microbiome. When we look at the scale we want to go to, we certainly want to have a deconvolution factory. This is not a lab. This is a factory environment that processes this material to get at those molecules. And we want to have a harvesting capacity that is 10 times what we currently have today. At 10 times where we're at today, there is not a small molecule in a microbiome that can hide from our technology. Ultimately, we look for a technology that can be taken around the world to look for these opportunities. In this next one, we're going to show a little video of one of our harvesting sites, and you're going to see a wide variety of things, and I'll try to do a little explanation as you see it. But typically, we can go to a wide range of environments. This happens to be a eutrophic lake that is got a toxic algae bloom occurring. Now, what can be interesting about the cyanobacteria toxic algae blooms is it's a warring environment. So there's a lot of microbes, a lot of organisms that are trying to survive in this environment, repair in this environment, and communicate in this environment. And the types of molecules that we could find are directly related not only to health and agriculture, but sustainability and other opportunities. So let's hit play. And what you'll see is you'll see our harvesting technology, which is a very large operation. And we will process 2 million liters in one day, removing 100% of the microbiome. Now, what you see in these two photos is you see slime on top of the lake. We don't go for the slime. We're looking for the living, breathing microbiome that is part of the waters themselves. And when we process this, we get everything from the virus sizes up to 100 microns and ultimately preserve it rapidly without lysing any cells. That's key in order to get at the small molecules itself. Now, pulling water of this type of microbial density into our operation is intense, and it can collect quite a bit. But as you can see, the water coming out of our operation is absolutely crystal clear. And you can see it mix here in a second with the lake water, and you really start to see the plumes of microbes as the water mixes right here. quite interesting. Microscopic organisms and clean water, it's obvious to see what's actually going on in that water is it's a wealth of microbes. Ultimately, the objective is to chill the microbial paste, which we turn into a high concentration solid rapidly, and then freeze it so that we really capture the metabolites from the living, breathing microbiome itself. Once we freeze it, we will ultimately end up lyophilizing it and going through a number of other processes. So what are we talking about currently and what are we talking about in the future? Well, right now the process is completely chemical free, so we don't expect ever to use chemicals in this process. We've been approved to run this process even in a marine sanctuary in California, where we ran it under state, local, and federal approval. But a typical full-scale recovery is equivalent to 8 Olympic-sized swimming pools. Literally a drop in a bucket when you compare the scale of, let's say, Chesapeake Bay, which is what you're seeing here. Ultimately, we can imagine going to 10 times this scale. And again, 80 swimming pools in something like Chesapeake Bay will have zero impact on the environment. One could say, unfortunately, it will remove out that microbial biomass, but that microbial biomass that we remove gets replaced at the rate we remove it virtually. So there's really no impact. Now, if we were recovering from a very, very small body of water, we could potentially clean the water to some degree, but that's not likely an interesting habitat for us to do a recovery to find novel small molecules. Now, when we talk about the extent of novel small molecules, this is just a sampling from the Natural Product Atlas, which lists 32,552 known microbial-derived natural products. And the chemistry across this that is produced from the known microbes, as well as the types of microbes that have been recovered under traditional technologies, really has left major gaps in science and research. For example, one recovery of a microbiome in the natural world has shown 73,000 novel molecules. Ultimately, one microbiome can double the amount of, actually triple the amount of known molecules from microbes. Now, I would also point out that microbes have been a prolific source of product production, whether it's in any of the life science areas, especially in therapeutics, putting nearly 50% of the products on the shelf directly, indirectly, or inspirationally. So when you start to talk about mining the microbiome for the hidden molecules, this technology is going to have a massive impact on creating multiple product categories across all of life science. Now, one of the ways that it really accelerates is utilizing the state-of-the-art technologies today enhanced by industrial scale microbiome mining. So synthetic chemistry, synthetic biology, other indirect omics, and then machine learning and AI data sets are all dependent on what indirect data and what culturing data has been obtained to date. All of that will accelerate rapidly advancing opportunities. One example of that is a substructure called indole. Indole is a part of a molecule that is very bioactive. Some of those are drugs on the shelf, but there's 4,100 known indoles that are naturally made today. In one microbiome, we found at least 1,500 new novel indoles. So that starts to give you the scope of the potential and possibility. Now, what I'll point out about machine learning and AI data sets, because certainly AI is getting on everybody's radar, is There is so much synthetic data out there that it can really confound the opportunity to discover. And what I mean by that is there's one company in China that's produced more than 2.5 trillion synthetic biology created molecules. Virtually none of those really represent what's going on in nature. So when you have virtually a infinite potential of data set, it needs to be honed to what is more real. And that's what industrial scale microbiome mining will do. It will increase the quality of the data sets for discovery dramatically. So how does Biosortia work with the world? So when we talk about ideation and collaboration, we want to work with the world to solve problems. So certainly we know our molecules can go into any of these fields, whether it's to help advantage our warfighter, new materials, advanced energy, agrochemicals, or therapeutics. And the reality is we don't want to be the developer. We want to work with collaboration partners and discover. So we work with academic partners and collaborators, and we work with industry partners. Ultimately, we want to help solve the biggest problems, the highest value problems that industry and government has, and that's how we want to work together. So now let's talk a little bit about the sustainability, environment, and agriculture. And let's do just a little bit of ideation. Let's look at just red tide. Well, red tide has been in the news the last 10 years because of Florida. Quite frankly, it's been an issue for 30 plus years. And there's places around the world that red tide is every bit as bad there as it is in the US or it is in Florida. But let's think about what could be done to really understand the organism and the opportunity to mitigate. Quite frankly, the opportunity is to study it in a scale that's never been achieved. If we can obtain the small molecules of the brevetoxin producer, we're at a point where maybe we could find molecules that could help inhibit it or help advantage other organisms to outcompete it. And if we study the red tide blooms themselves, we may find new opportunities across a number of industries, whether it's environmental monitoring, agrochemical and other biotechnology, or pharmaceuticals and therapeutics. The wealth of novel molecules potentially coming from a red tide could create billions and billions of dollars of new opportunities. And that's part of what we're trying to point out is when we've never had the chance to do deep chemical exploration of these kind of habitats with these kind of microbiomes, the knowledge is virtually non-existent. Let's talk about heavy metals as a potential remediation. What you see in this chart is you see the number of scientific papers that are talking about microbial remediation of heavy metals. Well, it's grown quite dramatically since 2000, and that's one of the things that is well known about microbes, whether it's microalgae, fungi, yeast, or bacteria. They really are capable of remediation of a wide variety of opportunities. But let's look at it differently. What if we knew the enzymes? What if we knew the molecules that were part of this? Then you could create industrial scale processing systems. It's great to be able to use bioremediation to do this, but it is also great to understand the chemistry behind it, the molecules behind it, because then you could probably capture things more efficiently, more effectively, and it might even create new opportunities for utilizing metals within the environment and capturing them or other toxic waste. And I think that's part of the ideation possibility here as well. What will these molecules and enzymes do now that we have direct access to those molecules? Another way to look at it is what kind of microbial molecules and discovery opportunities are there? Well, you've got to look at what has already occurred. And what we see from what has occurred is a wide range of opportunities. Just in the agricultural space, you've got insecticides, so different pesticides, fungicides. You also have herbicides. You have ways to enhance growth itself. Those are all opportunities. And that's one of the things that comes from these kind of molecules is you're talking about a wealth of opportunities within the agricultural space. Now, what's interesting specifically about the agricultural space is less than 2% of the molecules are on patent today. So the vast majority of agrochemical products, some of those are actually very dangerous, have gone off patent and need to be replaced by next generation opportunities. And we would say having new access to potentially millions of microbial small molecules that researchers have never had their hands on could create those next generation opportunities. When you talk about the whole range of opportunities, I'm certainly not going to spend too much time on this slide. We will post the deck itself, but across sustainability, the environment, or agriculture, there is such a wide-ranging opportunities from microbes. And many of those are inspired by what has already occurred from microbes to make products. So what we would like to say is this vast diversity of the microbial world is only partially explored, probably less than a fraction of a percent. So industrial scale microbiome mining will provide a massive increase of access to molecules that have already been pre-optimized by nature, by biology, by cells in order to work. Those are going to be critically important in the future of all life sciences because it's going to certainly increase the diversity of the bioactive compounds available. It will help identify novel modes of action, certainly create sustainable agrochemical solutions, and it will enhance our understanding of microbial ecology dramatically, and certainly precision agriculture as well as precision habitat control. So we're excited about the opportunity of industrial scale microbiome mining. Nobody in the world is being taught this technology right now, not at any university in the world, and certainly nobody is practicing this technology. Nobody would go mine lithium with a beaker. We suggest that the mining of the small molecules on this planet made by the microbes can be done in an environmentally friendly way and advance research dramatically into solutions humanity needs. So I'm going to close right now and open this up to anybody that wants to ask questions. And let me stop sharing. There we go. Can everybody hear me? Or can anybody hear me okay?
I can.
Excellent. So we will certainly open this up to questions. I think Eugene probably will facilitate the Q&A, but we'll open it up now.
Oh yeah, the first thing I was going to do was ask Steve Moretto to turn his camera off. But I think he did that. Okay, so anybody that has any questions for Ross? I know we had a couple people that raised their hand at the start of this that were here to see Biosortia and Ross.
I see a couple people in the audience that I know personally, so thank you for joining today.
Well, call them out.
Lan, would you like to ask any questions in this forum? I'll ask James Sanders. James, do you have any questions you'd like to ask in this forum or any comments?
We got Brian has a question.
Excellent.
Go ahead, Brian.
Hey, Ross. Ross, can you hear me?
I hear you great.
Great. So I have an interest in your technology in a few different areas. One would be possibly in cleaning textile dyes from wastewater, which is very difficult to do.
Mm-hmm.
Another could be in like a flocculant or a clarifier for metal mining wastewater discharge. If you were mining gold, mercury, whatever it was, your discharge water is almost always the most expensive problem on the mine site.
Okay.
Yep. And then one last one would be, what temperature ranges do you like to work with the water? Can you work with any water as long as it's got algae in it, or is there a temperature break?
Yeah, no, that's a good question too. So microbiomes around the world operate in a really wide range. So you've got thermophiles, and then you've got streamophiles, even in the very cold end of the spectrum. Antarctica has microbes that are part of a microbiome there. And when you think about the microbiome, a lot of people say algae. It's not necessarily photosynthetic organisms. It certainly can be organisms that are not dependent upon photosynthesis for their energy. And that's the beauty about all microbiomes. The microbiome of our gut is independent, or let's say indirectly benefiting from photosynthetic organisms in what we eat and what we consume, but yet it will process that without any ongoing photosynthesis. And the same thing about the microbiomes of the world. So our major goal in advancing this technology is to find partners that have valuable reasons to do something. So if there's a potential partner in the mining industry that says, we want to do this, or the textile industry that says, we want to do this, we would like to be able to start a relationship with them, move forward with that relationship. And then as we're fully executing the industrial scale microbiome mining, not only for the small molecules, but for the other opportunities. It's estimated that the aquatic microbiome has more than 1 million unexplored enzymes. So why enzymes become important is that becomes part of a potential processing system to do some of the things that's desired when it comes to remediation or the potential recycling of materials. Until that work starts, and our typical way to start that work is with researchers that could be in the academic environment, and then ultimately development of screening methodology that allows us getting closer to a target molecule that will do what we need to do, or a series of target molecules that will do what we need to do, so it can be turned into a process. And everything you just described needs to be turned into an industrial scale process, call it an advanced tertiary water and wastewater system that has the right processing systems to do the works needed. Is that fair?
Yeah, that's perfect. I'm especially, I can really see the textile industry somehow being able to recover valuable product and discharge clean water, and then hopefully it pays for itself.
That's the goal. And the nice thing is, a lot of these industries that have a high cost of waste handling, the way it really needs to be looked at is not just as a disposal part of the process, but exactly what you said, a recycling, reuse, cost-saving advantage.
All right, thanks, Brian. Chris, you had a question? Chris that came in?
Yeah. Hi, thank you. So I wanted to ask whether you've made contact with any of the with like the biotechnology offices within OUSD R&E.
We have not, that I know of. I've not heard of that alphabet agency, but would love to be introduced to them.
Yeah, that's great. Well, perhaps I could get well, I've got your information on the invite here, so I'd be happy to forward that information to the responsible party, and that way they'll know about what you're doing. Over.
That's fantastic, and we'll take a look online and see if we can figure out what they're up to, so that we could be prepared to have an initial conversation. That'll be great.
Right. They're the Office of the Undersecretary of Defense for Research and Engineering, and the office that I'm trying to patch you into would be under Critical Technologies, the Directorate of microbiology.
Brilliant.
Where
No, that's
Fantastic.
fantastic. And I think one of our challenges, Chris, which I think you recognized right away, is that when you have a novel new technology that's not being taught or practiced, yet it has this potential opportunity to impact all of life sciences, it needs the kind of engagement and support that can move it along rapidly. So I really appreciate that.
So one of the things that they do, they might not have the resources to fund anything directly, but they might refer you to one of Defense Department's manufacturing, um, what do you call it? Anyway, there's some
The
agencies
industrial
that are
base,
set up.
the defense industrial base?
No, there are these institutes
Oh,
for
yeah,
particular types of
right, the
manufacturing.
MIIs. You're talking about the
Right.
MIIs,
Yeah. And
Manufacturing Innovation Institute.
you got it. You
Yeah,
got
we're
it.
tied
And
in with
so,
all of those, that, the forum.
yeah, so they might say, hey, you know what? This looks good. We can't do anything with it, but we recommend that you contact, I think it's called Biomade or something, and that's one of the defense MIIs. So
Excellent.
thank you. I'll work on that.
No, I appreciate that. And, that's one of the things about this world. And I think Eugene went into that quite extensively during his presentation, is the socialization of these kind of opportunities. Many of the people we introduce this to have never heard of it. And I can understand why. It's so hard to keep up with what's going on. And when it's a breakthrough technology, it always starts really, in the corner of, let's call it, a large space. And therefore, it's not easy to pick up on or see for a while. So accelerating it through socialization is perfect, and we appreciate that.
Brian, did you have something else? Your hand was still up.
I pulled it down. Thank you.
So anyone else? I think was it Clinton? Did you raise your hand at the beginning of this, that you were interested in Biosortia?
Clinton
No.
is actually, just to let you know, Clinton is actually our head of our harvesting. So he's
okay.
he's part of our team. He may have thought of something we should be saying to this group, but he's always welcome to chime in.
I got one more thing.
All right, Brian.
Hey Ross, there is a place in Kansas. It's called the Great Plains Industrial Park. It's formerly it's a federal army ammunition plant. And most of the some of it they still doing ammunition, but most of it they're trying to switch over to private industry. The tax incentives are phenomenal. It's almost like their own little town and community with their own building codes and everything. It's really great. When I was there, there was a discussion about them wanting to improve the sewer and septic processing plant, and instead of just dumping the wastewater into the river, they were thinking about how to further extract possibly hydrogen from the sludge, and even to make different kinds of fuels, alternative chemicals. If you could look, if you're interested in that, I can connect you with them.
No, I appreciate that. You bring up a really interesting point. There are microbes that can produce hydrogen. So if there's microbes that can produce hydrogen, there is a enzymatic pathway, a production pathway that could potentially do the same thing. So even when you talk about advanced energy on the scale of hydrogen production, what could happen is maybe those chemicals are more expensive than the actual production itself. But if it uncovers pathways that are unknown, because microbes can do it in an efficient manner, that's knowledge that humanity needs to have regardless. So microbes can do a variety of tricks. One of those is produce hydrogen.
All right, Nick, you want to turn your camera off?
All right.
Nick is our next presenter.
Excellent. Well, I will get out of the way then if no one has another question. Fantastic.
All right. Well, thank you very much. It was Ross, Biosortia, fascinating technology, fascinating applications. Can see that creating a whole new industry and developing new technologies, new drugs, new everything. So I've been excited about this, and they will be regulars on our forum